Why don't we get started? How's your weekend? Good? Nice. Feel like a weird semester. I don't feel we haven't done enough yet. Then we got a break. So it's kind of upset my momentum. Um, but anyway, so it's actually nice to have a break early in the semester. But from this point forward, I counted like 11, 12 weeks without any break until Thanksgiving. So let's just hang on. Um, I uploaded the first homework, which is pretty straightforward. I realized I didn't really give you an announcement. Apologize for that. But if you haven't noticed, there is homework number one. As I promised, it is a simple exercise on Python programming. And the real purpose is for you to install Jupyter Notebook locally, get your hands dirty if you haven't done that before. Just write some codes, turn it into a PDF. I very much insist on you submit a PDF as well as a Jupyter. I like to annotate your work. It's impossible for me to annotate on Jupyter, so I need you to submit a PDF. If you are not familiar with Python and you need more time, that's fine. Just let me know. Okay. Otherwise, I expect you to deliver this weekend. Oh, sorry. Send me email. Send me email. Let me know. Okay. All right. I want to remind you about the coffee. Yeah. The coffee hours. Okay. Right now it's okay. I entertain 4 of you on the average, 4 of you per week. That's still within my limit. So that's just continue to make appointment with me. I really like to talk to all of you at least within the next 4 weeks, 5 weeks. Okay. Our class size has reduced to 32, which is good. It's exactly the same number as last year. Okay. At one point it was like 38. So, wow, that's too many. But anyway, make an appointment with me, have a cup of coffee. Okay. Let me get to know you. All right. Before we start, I saw something that's really interesting. I'm not sure if you catch this news about first kind of Olympics, first kind ever for the humanoid robot games held in China just a couple of weeks ago. I thought it was pretty fun to look at it. Just a few minutes. Let's have a look.
This is not your average sports tournament. At what is billed as the first ever.
Give me a second. Let me get a sound out. No sound. The network. Second. Hmm. Yeah. Sounds feels like I'm losing the network. Just a second. Shoot.
This is not your average sport
Couldn't find the speaker. Okay.
tournament.
I'm sorry, I just have to
What is billed as the first ever World Humanoid Robot Games. The athletes come in all shapes, sizes, and structure to compete in events ranging from running to kickboxing to soccer. For 3 days, human handlers from 16 countries are putting machines through the motions to show the potential of embodied AI as well as its limitations. It isn't about winning or losing, but it's a way to trial the robots in agility, endurance, and battery life. Some of the humanoids are competing in more practical job skills, like sorting medicine and hotel concierge duties. That's why a team from Starbot made the trip from California. Their robots work in customer service.
Do you think humans are ready to have robots so involved in their daily lives?
I think so. As a matter of fact, our company already works with restaurants and we already have robots providing service to customers and they are welcomed really well. So I think perhaps not everyone, but I think we are ready as a society to incorporate robots into the environment.
The games are meant to showcase how far robotics have come and to provide a window into a future where humanoids are integrated into daily life.
But it also reveals how heavily China's government has been backing the development of these technologies to close the artificial intelligence gap with the United States. For years, Beijing has been funneling tens of billions of dollars into AI research and state subsidies, like it did with the electric vehicle industry, making all this a very different kind of race.
Videos of robots dancing, punching, and performing have been all over Chinese social media and state TV as the government has deepened its investment here. But the games are the most ambitious promotional push yet that drew a small but curious crowd to watch how next-gen robotics are taking shape. Research published by Morgan Stanley predicts that by 2050, China will have 302.3 million humanoid robots in use, well ahead of the U.S. projection of just 77.7 million. He says when robots like these gain independent thinking and behavior after training, that will be the real AI age. From what we saw here, people are not obsolete quite yet. There were no speed records being set, and many of the athletes, well, they're prone to fizzling and faceplants. Yet it's all wired to the real goal for China, getting ahead in the global race for AI domination, one clunky step at a time. Janice Mackey-Freyer, NBC News, Beijing.
We thank you for watching, and remember, stay updated on breaking news.
What do you think? You will. Well, it's actually not a surprise that this happened in China. Okay. China tried to catch up with US and Europe in terms of AI advancement. And I have to say, in humanoid, I think they are ahead. And they are using their manufacturing capability to manufacture as many robots as possible. So that is coming, that's for sure. Okay. But let me ask you a question. Are you ready to have one of those in your house? No? No? Okay. Yeah. I mean, they still seem pretty clunky and awkward. But if you think about some of the more reasonable applications, I think, looking at the robots competing with each other in a sports arena, it's a little bit far-fetched. There's one, it didn't show here, but there's one viral clip showing one of the robot when it's running the 1500 meter. The robot fell and lost one of its left arm, I think. Well, not completely lost, but kind of fell off, okay? Because he fell. I say it fell, okay? But robot, being trained by reinforced learning, find its way to get up. It actually get up. Some of the viral clip actually show the robot, kind of like feel like a drunken driver, a drunken sailor, staggering around the track and hitting people actually. But eventually the robot finished the race. And guess what? Just like we cheer for a human being, the audience cheer for the robot. That finished. Okay, so that begs the question. To which point we treat robots emotionally, treat robots just like a human being. I feel like it's coming. The funny thing is, we feel for robot when it fell, but robot will not feel for us when we lost the job because of robots. Isn't that real? Very real. The other funny thing I heard this morning is there are a product called Robot Boyfriend in China, actually sells pretty well for girls. Wondering what can that robot boyfriend does? All right. That's just a very, very funny side news. But I was sidetracked a little bit. But if you think about more serious applications, there are scenarios that robot actually can help a lot, right? Helping people to lift heavy stuff. That's already in the making, but we just now turn it into a human-like robot, right, that can help you lift your heavy luggage, whether it's in the hotel or in the airport, right? Helping, senior center to take care of the seniors, right? Who usually need nurses and helpers to take care of their daily lives. But right now, at least we can imagine robots running around the facility helping seniors. And I also heard there's actually one facility in China, a small hospital, still early in their trial stage. They got no human beings. All of the patients there are treated by robots. So I cannot imagine how that works, but it's coming. All right. So let's recap what we left off last time. Let me just recap the structure of perceptron. Okay. So this is a single layer perceptron. In the middle is a neuron, and neuron does two things. Can you, what does it do? Say again. All right, so two parts, right? The first part is to calculate based on the input features and calculate the linear weighted features. And add them together. And that information will be passed through the second part. What do we call the second part? What's that? A. What's that second part of the neuron? This activation function. Exactly. So shorthand notation for activation function is A, being the outputs. A equal to FZ. You take Z, which is the output of the first part, and pass it through an activation function represented by F. An output is called A. So A is essentially your output. So that's a basic construct of a single layer perceptron. Then we also talk about the multi-layer perceptron, MLP. So what is MLP? What do we add compared to? We add hidden layer or hidden layers depending on the depth of MLP. So between the input layer and the output layer, there could be multiple layers of hidden layers. So those are the terms that we talk about in describing a neural network: the depth, number of hidden layers. Okay. Of course, plus the output layer. There's always an output layer. And the width is associated with the number of neurons in each hidden layer. That's called width. Okay. And the total number of neurons determine the capacity of your network. Obviously, the more the neurons, the better, the more powerful of your network computation capability. Of course, that means complexity. That means computing power being used by your computer. Hey, we also talk about one case that's describing MLP as a universal Boolean functions. As a matter of fact, we will continue to finish this part using 3 cases. So the first case is we can use an MLP to describe any type of Boolean function. Okay, so how do we do that? How do we actually do? How do we actually come up with a Boolean function? We started from a truth table, right? A truth table describing the relationship of the logic output versus the input, which of course is a logic, also binary input. So you have a truth table. Then you describe a Boolean function based on the ones that you want to, the logical one output, right? Or you can also look at it from logical 0. That's your Boolean functions. And we prove that you can use, starting from the truth table, you build a Boolean function, and you can build a one hidden layer neural network using AND gates and OR gates. Right, so far so good. That's a recap of last Wednesday. Make sure that you remember that. Today we will move on to another case, which is to use MLP as a classifier, universal classifier. I want to look at several cases to see how MLP can be used as a classifier. Okay. So go back to this basic structure of a single layer perceptron. The output, not at this moment, we haven't really talked about other activation function other than thresholds, right? Logic threshold. If the Z is greater than a particular threshold, then we fire up, activate the perceptron, the neuron, and we'll make the output 1. Otherwise, it's 0. So it's always binary, 0 or 1. Okay. So I want to show that essentially this structure is essentially a linear classifier. Okay, let's look at some very simple examples. Just two variables, x1 and x2. We have 2 input features, x1 and x2. And for x1 and x2, we associate each one of them with their corresponding weights, w1 and w2. So that's your basic perceptron. Okay. So now the Z, that's just the equation. Right? Z is equal to w1 x1 plus w2 x2. That's a linear combination of the 2 inputs. Okay. And T is the threshold. So obviously T is that decision boundary, right? Because bigger than T, A equal to 1. Smaller than T, A equal to 0. So this line, Z equal to T, is the decision boundary. Agree? Pretty simple, right? And that decision boundary will separate 0 and 1 output. So over here, I kind of define what is a decision boundary. Decision boundary is in a 2-dimensional space is that line, which show in this case a line that separates the entire space into two regions, 0 and 1. Or if you have a multi-dimensional space, a little bit harder to imagine multi-dimensional when it's greater than 3. But when there is a multi-dimensional feature, we call this hyperplane. That actually can decide the decision boundary. But at the end of the day, decision boundary are the lines, whether they are 2-dimensional or multi-dimensional. Their job is to separate the data points into different classes. So for this very easy, simple exercise, the decision boundary is right here, this line, right? You know that the right-hand side in the pink region, that's where 1 is. And below that, that's where 0 is. right? So just give you an example. They ratio equal to 3, both weights are 1. So pretty simple. You know that this blue line is x1 plus x2 equal to 3, right? Suppose that, because that's the decision logic. So in order to actually draw this line, it's simply, not switch side, you x2 equal to minus x1 plus 3. So that's the line, and everything on the right-hand side is a 1. Will come out as 1, and the other side is 0. Okay, so it's pretty simple. Dimension using a straight line. Decide this to have the decision boundary. This is kind of go back to how we can also interpret the Boolean function using those real input two-dimensional features. So if you remember, for Boolean inputs, if we have two variables, we have two possible values, right? 0, 0, 0, 1, 1, 0, and 1, 1. And you can put them in those two discrete points. Right. So what is this? The first function. What is the first function? OR. The OR gate. Okay. Why is that an OR? The first one on the left-hand side. Why is that an OR gate? Because if you add x1 and x2 together, and they are greater than or equal to 1, then we define that as 1. That's how we decide. That's how we define that special logic for the OR gate. So those three conditions, obviously, they all result in 1. So that's an OR gate. This OR gate is that either one of it is 1. You get output of 1. So what's the second one? What's the second logic function on the right-hand side? And, right. Because only when both of them are 1, it's a 1. Otherwise, it's 0. It's an and. So that's just kind of a confirmation that you can also use a classifier using real number to represent the Boolean function. Okay, now I'm getting interesting here. If I give you an arbitrary, in this case, the pentagon, right? You have a pentagon in the middle that separates your orange dots from the blue dots. Okay. So it is a very typical nonlinear separation of classification. This is nonlinear classification. This is not one simple straight line to separate blue from orange. So how do we actually use MLP to construct this boundary? Okay, so that's a question. Any thoughts?
As far as definitions, we have a bunch of piecewise linear functions.
Yes, that's very good. Because here's the thoughts, right? Because we just showed if you have one straight line, you can take a cut. You can take a cut of the entire signal data set space. So what if I take multiple cuts, but those cuts are different? We combine them together. So that's the basic thought. It's very good. But how exactly would do that? So that's exactly what Tim just said. Okay, we can use one single perceptron to represent one decision, one line. So potentially you can use 5 of them in this case. Right? Each one of them represent different decision boundaries. So somehow, if we can combine them together, you probably get your solution. So let's just give this a try. Okay. So let's just say, our first slide is the one across the x-axis. That's our first cut. That first cut is a single perceptron. Let's separate the data set into 1, 0, and 1, upper and lower, right? So you start to get the idea. What will be the second cut? And you cut it this way. You cut it at 45 degrees. Taking care of side number 2. So you add another perceptron. So also good? Does that make sense to you? Okay. Those two are dealing with different sides. They are different decision boundaries. So if you follow me so far, you know what's happening next. Is that you have the third perceptron. Yep. You also have the fourth perceptron. Eventually, you have all the perceptrons. You have all 5 of them. Each one of them cut one side of the pentagon.
Wouldn't you have another percentron for evaluating all the outputs of those?
We'll see that very soon. Okay. So now you have all 5 of them. Together, create this boundary of pentagon. Actually, end it in the output. Why n? Either or n, right? I'm not going to confuse you. Why do you end the output of those 5 together? This conceptually, each line is separate.
It needs to be confined within the variable.
Exactly. Exactly. Those 5 slices need to confine the overall results into a pentagon. And the only way you can do it is read end results. You look at it, this first cut separate in 2 sets, right? Z equal to 1 is on the upward. And the second one kind of cut it to 45 degrees, and Z equal to 1 is on the left-hand side, and vice versa. Each cut create a Z equal to 1 region and 0 equal to 1, 0 region, and you have to add all the Z equal to 1 region together, so you get that pentagon in the middle. Right? So a perceptron. So now we have an NLP structure to actually make this boundary possible. The side question is, what are those numbers? I put a few numbers here. So obviously, the one in the middle is 5. That means this is the one that every slide, every slide will create a result of Z equal to 1. So that means 5 times right in the middle, the number of the times the neurons are actually activated. So use the term activation. Only over here, that's Y1, Y2, Y3, Y4, Y5 are all active. So you can add them together. The other ones, you only get 4 times, so they are not exactly inside the pentagon. Some of them are 3, that means they only got 5 in those 3 out of 5 openings. Okay. So when you equip with this possibility, how do you do this? Well, you know how to do the lower part, right? But the upper part is just another pentagon. You know, you're onto something. So we know how to do the lower part. The pentagon in the lower part is called solid, right? So we have one MLP on the previous page. So the second one is also a pentagon. So you know there should be another MLP. Then what's the end? Yes, you combine them with or. Right? Because either this or that. I think either this or that. But yes, you have two pentagon. You have two MLP that can decide to give you a pentagon with two boundaries. Then you combine it at the end, or them together. All right. We can keep going. We have 6. What do we call 6?
Yes,
6. Similar idea.
how would we do like non-linear functions, like as in like circles, or
Because we keep going, right? If you so you continue to add the number of what do you call that? Sides, right?
Yeah.
And continue to add sides. You potentially make it 64. Then what? When the number of sides increase,
it goes to infinite, it becomes a circle.
it becomes a circle. Yes. So at the end of the day, when you have infinite number of sides, it becomes look at numbers of you increase the number of neurons in this single hidden layer MLP. We can keep increasing the number of neurons in that hidden layer. You add them together, so eventually what you get is boundary of a circle. And everything else is pretty much the same. So that's an intuitive way to look at classification using MLP. Okay, what MLP can be a good classifier. Okay. Now, of course, we can think about multi-dimensional, which is use 2-dimensional in view intuition. But when you increase the number of dimensions to 48 by 28, which in this case is actually a digit recognition problem. So why can we actually recognize a handwritten digit like this? This is a 2. Whether you like it or not, it's a 2. The classical data set actually make 28 by 28. So this is a 28 by 28. What do you call that? Pixel. 28 by 28 pixel. So you make each digit a 28 by 28 pixels. And so 28 by 28, each one of them is an input feature. So you have your input feature has 784. Don't be alarmed by the numbers, but that's actually how it is. So your input layer potentially has 784 features, not 2, but 784. So you do have a large dimension. I use this very silly 3-dimensional plot. It's actually not 3-dimensional. It's actually 784 dimensions. Okay, but conceptually, you use an MLP to create a decision boundary that will result in a decision that this is a 2. The rest is not 2. So of course, there's a big jump from 2-dimension to multi-dimension, but the idea is very similar. You can use many dimension in the input layer and trust that your MLP, however complicated it can be, will eventually come out with a decision, an output layer, which in this case actually is multiple layer, multiple outputs because we are trying to recognize 10 digits from 0 to 9. Okay, so we can go pretty deep in terms of theory, but I prefer to give you intuition. Two-dimensional example is an intuition. It's good intuition. Tell you a classifier can be implemented by MLP, which is a big deal because a big part of neural network is to do classifications, image classifications, speech classification. At the end of the day, we are trying to find out which class, which decision is the eventual output. Okay. The third one is probably the most important one, is to introduce you to the concept of universal function approximator using an MLP. Okay, so again, there are a bunch of theory behind this, but I want to make it a little bit simple. So let's just assume we have real number input and real number output. Both are real numbers. And for a classical math problem or functional analysis, we try to find an f, a function that can map x to y. This is essentially our learning problem as well. Give you observation of x and y, you come up with an f that can map x to y. So that's essentially how we want to solve this problem. Now we want to use MLP to solve that problem. Let me introduce to probably the only theorem that you are going to encounter in this semester. It's called universal approximation theorem. I only give you the state. I'm skipping the math. I will give you examples, intuitive examples to kind of get you the idea. So UAT pretty much states that a feed-forward neural network, which is what we have today, feed-forward. There are some feedback neural network, which is what we introduce later in this. A feed-forward neural network, which is a classical neural network. With a single hidden layer, we're not talking about multiple hidden layers. We're just talking about one single layer. Okay. And activation function. So this actually something addition to the condition. Hidden layer plus a nonlinear activation function. And if you have sufficiently large number of neurons in that particular hidden layer, then this MLP structure can actually approximate any continuous function, an arbitrary degree of accuracy. That's a statement. Is the statement clear to you? No? No? Okay. So I will give you some examples. But let me just say it again. In plain English, this pretty much means that any single hidden layer MLP can approximate any real continuous function. Whether that's a sine function, easy, right? Sine function, or a multi-dimensional, multiple degree of polynomial functions, or math functions that you know. Okay. So that function is any function, and you can make it as accurate as possible, but you'll never get to exact. But I think we are happy if we are getting really close in terms of accuracy. So why is that an important statement? Because this is pretty much the theoretical basis for us to feel confident, right, that neural network can actually perform exactly what we expect the network to perform. And we can pretty much use neural network to learn any function. Think about it. You can pretty much use a neural network to learn any function. That's a huge statement. And that's why we should feel comfortable use neural network to solve. I wouldn't say any because there should be some exception. I'm pretty confident. Whatever problem you are going to solve, neural network has a solution. That's the importance of this statement. Okay, so if you think about the task that we are dealing with regularly, like image recognition, natural language processing, or even the game of Go, they all can boil down to some underlying math structures that we just don't know. Okay? It could be really complicated. They don't have closed form, but they do have a structure. Even though there is no closed form, it is still a function. Don't think about just closed form as a function. A function is just something that can map x to y. Okay? So if you think about it, image recognition has an underlying functional structure. NLP can figure it out. So that's the most important implication for this theorem. All right, so prove it, sir. Now, how do I know? I'm going to give you a one-dimensional example and intuitive explanation. Okay. So we want to use MLP to generate a pulse. For SWE, you know what a pulse is, right? A square wave, for example. In this case, we are generating exactly a square wave. So how do we actually generate a square wave using MLP? So here is an example, a function that can be realized by a math function, right? The signal that can be generated by an MLP. So can we convince ourselves this structure can actually create something like that on the right-hand side? Let's look at it. Right? In the upper side, right? You have a hidden layer. This is still expression. Alpha being the expression. So, and there is an activation function. So that pretty much means that if your x was multiplied by 1 is greater than alpha, then we fire up, right? And we set it as 1. So that's why we have this kind of step function in the upper side, right? So similarly, in the lower side, if x is greater than beta, then we fire it up. So you have two step functions, one in the upper, one in the lower. So in order to create a square wave, how do we actually use those two step functions to come out with a square wave? So the answer is, if your x is between two of them, right? Between alpha and beta, then you have this. So you use this MLP structure to create a pulse, which is the basic unit that we want to use to have a simple proof. Okay. So, hey, we use MLP to produce a circuit, but not a circuit. This the signal. Okay. So that is the signal that we are going to use. Okay. All right. So that's the explanation. We created a square pulse. We can actually make this pulse infinitely long if beta minus alpha is big, approaching infinity. And so this width is the width of the pulse. It's adjustable. You can make it, on the other hand, as small as possible if beta and alpha are pretty close to each other. This we can make it really small. We can make it really big. Okay. Keep this structure in mind. I'm going to combine two of those pulses together. Now you see on this one, we are combining two pulses One of them, I put real number here. One of them has 3 and 4, so it creates a pulse between 3 and 4. That's the upper one. And the lower one has a pulse between 7 and 8. I want to combine them together, but essentially because 3, 4, 7, 8, they are disjoint from each other, right? That disjoint wave. So from a time standpoint, they are being separated already. I can add some twist by adding an additional amplitude to make the pulse different in terms of amplitude. So that later stage before we add them together is actually adding the more information on amplitude. So potentially you can add a whole bunch of different pulses to create not a time series of pulse, right? Yes.
The waves, that were from the evidences of the policy.
Yeah, all of them are. All of them. But for the first one and second one on the left hand side, those they are just one, they're unit. But once you're on the second stage in the output layer, we multiply by different numbers. So that create that kind of differentiation in the amplitude from each other. Okay, so now we constructed a new signal that has 2 pulses with different amplitude. Okay, so I'm gonna ask you, this is something that you probably learned from your calculus 1, 2. How do you actually
So Riemann sum.
Riemann sum. Very good. So we want to approximate that blue curve. We call that GX. We call that GX. That blue curve is a signal, right? If you learn your calculus well, how would you approximate that GX? With the concept we just did. With the pulses, let's just look at pulses. It's integration, yes, but further, more thoughts? Can hear you. But if you just look at the way I draw it, for those polygons, those kind of squares, polygons, how would you do? How would you actually implement those polygons? This is one approximation, right? It's not exact yet, but I'm giving you 12 of them to approximate GX. That's one way to do it. So how would you actually create those 12 polygons? Of course, K1, K5, K12 are the entities.
Some of the areas.
Right. So the area under the curve of the GX kind of represent the value that you need to represent that particular region, right? So we just use a polygon to get close to it. So in this case, we can use 12. 12. And we'll create those 12 polygons. Right? So the first pair, alpha 1 and alpha 2, beta 1, alpha 1 and beta 1 create pulse 1 and multiply that by K1, that's your first polygon. Then you can create number 2. But all of them, of course, will be different. Remember, alpha 1 and beta 1 are the numbers that determine the time interval, right? If you make them close together, they happen one by one. I mean, that's how we calculate, that's how we teach calculus as well, right? Frankly speaking. So before I move on, can we convince ourselves we can use the MLP on the right-hand side to approximate dx as at least as one representation? Any questions?
Would be doing integration after a certain point.
It is, we don't do integration per se, but from representing a function standpoint, that's how we do it, right? That's the way to do it. Well, since Tim is mentioning integration, let me ask you this. You are talking about integration, right? Just say, I'm just gonna make up some number, okay? You want to integrate a function fx over a period from 0 to t. Numerically, how do you do it? Fx can be any arbitrary function. There's no closed form. So there's no way you can convert this using expression. But numerically, I'm pretty sure you guys all have learned how to do numerical calculation. How do you do this?
It'll be integral big F of t, f of x, or it'll be f of t minus f of 0.
So we eventually we turn px into a finite number we can understand, right? It's just delta x. If you want to make it fancy, the delta x can be different from one interval to another. At the same time, you take fx, you just kind of have
Integral.
hello? Anything you want to say?
I think it's the integral of calculate approximate integral of gx.
Right. So we're trying to use numerical methods to calculate the integration. Right. So I'm trying to kind of get equivalent methods to calculate. So this is n, right? So eventually integration is essentially the summation of infinite numbers. Yeah. Use I here. Anyway. So this n eventually will probably approximate infinity because that's where you make this polygon narrower and narrower. So yes, Tim is correct. This looks very much like integration. And we implement integration numerically. We actually write a program to sum up large number of very, very small delta x times fx. Okay, we're not done yet. So we can think about approximating gx using a structure of 12 network, right? MLP. Then how do we make this the precision arbitrarily small? And
Reducing the alpha beta.
increasing, say again.
Reducing the alpha beta.
Yes, reduce the distance between alpha and beta, meaning reducing the size of the width, right?
Yeah.
Of each polygon. Make it really, really small. And make the number of, essentially they increase the number of pulses. So that actually that's exactly what we did. Integration. We calculate integration itself. Right. So eventually this curve called gx when you approach me, the limiting case, theoretically, will be smoother and smoother. Right? Theoretically, it will never get to be zero error because you will always have a very small error, but it's close enough. So we say function approximator. We didn't say universal function. We say function approximator. I want to kind of stop a little bit, so make sure that we kind of absorb this concept. Very simple concept. Very complicated concept, but actually I use very simple example to illustrate. At least from a two-dimensional diagram, you can think about any continuous function as a linear combination of infinite number of those polygons. And you can make the error as small as possible by just increasing the number of polygons. All right? So after 3 weeks, you should be able to start to tell people why and how. If you just say those 3 things, all right, you're good. And because I can tell people you can implement any Boolean function using MLP structure. May not be the best, but you can find them. You can use MLP to be a universal classifier. And also, MLP can approach any real function. It's the most powerful statement at the end. Okay, something that I have to make a caveat over here is that the statement here is about using one hidden layer. Okay? But you can imagine, geez, that if I want to make the precision as good as possible, then I have to have a lot of neurons, right? So this theory doesn't really tell you if you can do it or not. You can, of course, do it. I mean, realistically, is it feasible or not? Can I have millions of neurons? Of course not. That's a waste. Okay. But theoretically, you can use one single layer with unlimited amount of neurons to implement all those 3 things that we talked about the last couple of lectures, right? But of course, there's always a but. We haven't talked about depth yet, right? I neglect to talk about that. I don't want to make things more complicated than it has to be. There's a depth we can explore. Once you kind of redistribute the number of neurons through increasing the depth, things will become much easier. Things will become much easier. That's something we will explore along the way. Anyway, okay? That makes sense? Good. I still get a few minutes. I want to kind of push forward. Okay. So the second topic here is about setting up the concept, so we can actually do the more important thing, which is the actual learning, the actual training. Okay. So still, we'll focus on the basic ideas. So the first topic is on forward propagation, and you will learn next Monday what is a back propagation. So those are 2 important concepts. So let's talk about forward propagation first. I want to kind of emphasize activation function first, because if there's no activation function, especially if there's no nonlinear activation function, there's no neural network. Activation function, you can think about that as a decision-making unit. We use a very simple decision logic threshold. Okay. To fire up, to activate the neuron. A simple activation. In essence, the activation function make a decision whether the neuron will be fired or not, or what kind of value would be output to the next stage. So activation function is very important. It's a decision-making unit. It decides what information can be passed to the next stage. Right? And from neuron to neuron, from layer to layer, what's important is the information being transferred, some of them being filtered in the earlier stage. Some of them kept going. Think about it. There's actually a lot going on in each neuron when using the activation function. All right, so we kind of experienced so far the simple conversion logic activation, and that's pretty good for linear classifier. We have seen enough of that. We use that to construct R-shape decision boundaries, such as multi-side polygon. And the question is, how do we actually do nonlinear decision boundaries? Nonlinear, without actually resorting back to linear boundary decision boundaries. Okay, so those are some very simple data set that I've shown before. How do we actually do this? The circle. How do we actually come up with a circle? This is a little bit more difficult. How do we actually come up with nonlinear decision boundaries to classify those data points? Right. So I want to emphasize the importance of activation function. So if there is no linear if there's only linear activation, meaning not nonlinear, only linear activation function. So essentially, you are passing whatever the value of z is to the next stage. So activation function pretty much means that it's equal to z. So if that happens, you can easily imagine that your output would just be some sort of linear combination of units, right? Because there is no nonlinear functionality between your input and the output. So in that case, you always end up with a linear boundary, decision boundary like this. You're never going to get something like the right-hand side, which is highly nonlinear, very curvy, right? To actually separate the green from the red. Okay. So that's why we have to talk about nonlinear activation function. Now we graduate from logic threshold logic activation for that linear activation. Now we want to look at some of the popular nonlinear activation functions. We are going to see activation functions throughout the semester. I want to give you a few examples that are pretty popular and give you an idea that why they are useful at the beginning. So there are four that we will introduce today very quickly. Two types. The first page, we talk about two of them. First type. So sigmoid. We talk about sigmoid when we mention the logistic regression. And the second one is called hyperbolic tangent, or we call that 10H. If you look at their plot, the way they look, they are pretty smooth, mapping the entire real axis into a fixed region, right? So for sigmoid, the entire x-axis is mapped from 0 to 1. So sigmoid is pretty good in binary classifications, deciding whether it's 0 or 1. Because sigmoid essentially gives us the probability of a particular class. And 10H also has the similar property, but instead of mapping to 0 and 1, they map to -1 and 1. Okay. So if you think about why those two are different, the only difference really is the mapping the output. So 10H has more versatility versus sigmoid in the sense that your output is balanced around 0. So they can take minus number, or they can actually output minus number, they can actually output positive, and they are average, centered around 0. So that's the major difference. But both of them have a limited output from either 0 to 1 or minus 1 to 1. So that's one type. The other type is increasing the dynamic range of the output. One of them is called ReLU, rectified linear unit. The other one is called leaky ReLU. Their difference is very subtle. You just look at the upper curve of ReLU. ReLU is essentially a simple function that if x is greater than 0, it's pretty much y equal to x. This is pretty much y equal to x if x is greater than 0. And if x is 0, is negative, that the output will be 0. So they have this kind of an elbow shape. L 0 and y equal to x. It's very widely used in applications such as image classification. Leaky ReLU is slightly different. Instead of having 0 for x being negative, they actually introduced a little bit slope in the negative portion of x. If you look at the lower curve for leaky ReLU, for positive side of x is still y equal to x. For the negative side, there is a very small slope, usually in the value of 0.1, even smaller, to allow the activation function to send some of the negative information to the next stage. Whereas for ReLU, the information of x less than 0 is lost. It's lost. They only send information for x greater than 0. So why is this useful for image? Like, can we use sigmoid or 10H for image? Of course you can. Of course you can. But if you think about image processing, each pixel is represented by 0. One is 0.
0 to 255.
RGB, right? RGB.
No, 3 colors.
For 24-bit colors.
Yeah, even it's black and white, you still have 0 to 55, as you said, right? So it is not a binary number, right? It is a real number. So each pixel has information that is important for making an image classification. So increase the dynamic range. So your activation output preserve the dynamic range. It's important. So that's why I look at activation function and I put them into 2 categories. Okay, so the first type has a limited, the activation output is a limited range, whereas the second page, the dynamic range is wide. This one is not essential at this moment, but eventually we'll see that. When we talk about training, we'll talk about a very important technique called gradient descent. And gradient descent pretty much means taking derivative of functions. So eventually we will need to make a derivative of those activation functions. And therefore, I just going to list the derivative at this moment. It's not important right now, but they all look very elegant. They all look simple and elegant. Okay, a couple more notes about activation function. So if we we use F throughout the semester. We use F to represent activation function. And we also use a superscript, a bracket L, to represent the activation function in the L layer. We have multiple hidden layers. So ideally, theoretically, the activation function for each layer can be different. Although it's kind of silly, but it's possible. Okay. Especially you definitely will have most of the time different activation function between hidden layer and output layer. So in most of the cases, all the hidden layers may use the same activation functions. So in this case, of course, we only have one layer in this situation. So we say, oh, okay, this is ReLU. ReLU, we use ReLU for the hidden layer. And the output, we use sigmoid. They are different. But we use sigmoid in output layer quite a lot because sigmoid allows us to classify. But that's one concept. You can have different activation functions for different layer. Okay. All right. So let me recap. Activation function enable neural network to learn the nonlinear relationship. Okay. Introduced by the nonlinearity of network. Activation function is essentially an information filter. Big concept. Because it controls what information can be passed to the next stage. What will be filtered out? That's very important. I want to spend like 3 minutes, the final 3 minutes, just to look at a very intuitively interesting playground you can play with. Okay? I think this is developed by some Google people or maintained by some Google people. So this is actually a training process. Some people wrote the code and do a training process. Don't worry about terms such as epoch, learning rate, activate, and regularization. Those are not important. Okay. Right now, I just want you to focus on activation, which is here. You can have a pull-down menu to change the activation function. And also in here, they give you a structure of the neural network you can actually play with. I'm going to just play with one hidden layer, but you can do this too. Okay, you can add layers, and you can also add number of neurons for each layer. Okay. For simplicity, I'm just going to using one hidden layer. Okay. They offer you several different data sets. So that's the circle one. That's the quadrant one, and this is the spiral one. This is the easy one. But anyway, so this is 2 dimension. You have 2 features, x1 and x2. There are some other nonlinear terms as well you can play with. Right now, just for demonstration purpose, just look at x1 and x2 as input. So that's your data set, right? Let's just we can play with different. Let's play with ReLU. That means on that hidden layer, the output, the activation function is ReLU. And the decision here, I believe they use sigmoid all the time. So let's play with it. Here is you just click the button, and you start to see the training going. You notice the change on the right hand side of the data set.
That happened instantly.
Huh?
It happened like almost instantly.
Instantly. And if you notice the above the data set, there is actually some metrics showing the error. It's very small, and it happened really fast. Right? That means ReLU works pretty well in this case. Did you notice there are 6 sides in the decision boundary? Right? Let's say if we do this and run again. A second. So we need to do this. Okay. Again, it's pretty fast. But now we have 5 sides. That's the characteristic of it. It behaves a little bit like the hexagon, the polygon, the polygon example that we have. Okay. The other thing you can also check, which I think is very instructional, very helpful, is to click on each neuron. Shows you when you click on each neuron is the decision boundary of that particular neuron. Okay. If you at neuron number 1 at the top, that's what the neuron is seeing. The neuron is doing this job. Okay. If you move down. All right, so that's why at the end we see this. Okay, this kind of justify, kind of align with the example that we gave, right? Now I want you to play with it and see the difference. Okay, see the difference. You see 10 edge doesn't have that very sharp edge, very smooth. So almost like triangle, that's pretty smooth. I encourage you to check each one of those neurons to see what kind of decision boundary that neuron will give it. So the intuition when we talk about classify is that each neuron has a job to do. And if you add all the neurons' jobs that all put together, you essentially will get the eventual classification boundary that we want. We actually will have more work on this next week's, but this is a pretty fun one to play with. Okay, I think we're running out of time. Thank you very much. Any question? Okay. All right, I'll see you next Monday. Okay.